All right, number 18, we want to factor each of these completely. So for this one, since it's a trinomial, the first thing I'm going to do, there's no greatest common factor between all three of them, so I'm going to build a bridge. That gives me a negative 10. The two numbers that multiply together give me a negative 10, but add together to give me this middle coefficient right here, the negative 3, are a negative 5 and a positive 2. So that means since there's a 1 out front, as my leading coefficient, I gives me my shortcut, so it factors into an x minus 5 and an x plus 2. That's it for this one. Number 19, I start off the same way. I build a bridge. I build a bridge that gives me a negative 12. The two numbers that multiply together to give me a negative 12, but add together to give me a positive 1, or a positive 4 and a negative 3. With this one, since there's a 3 out front, I can't use the simple shortcut that I did before, so I'm going to split up the middle coefficient. So instead of a 1x, I'm going to write it as a plus 4x and a minus 3x minus 4. So I've taken that middle term and I've split it into two separate terms. Now I can do factoring by grouping. So I group the first two terms together, group the second two terms together. Out of the first two terms, I can factor out an x, which leaves me with a 3x plus 4. Out of the second two terms, I can factor out a negative 1, which leaves me with a 3x plus 4. And now this is where the magic happens. I see the 3x plus 4 they have in common, so I can factor out that entire thing, the 3x plus 4. And if I were to take away the 3x plus 4, the two pieces I'd be left with are the x and the minus 1. So that's my other factor, is the x minus 1. In number 20, I notice right away that they have a 3 in common, so there's a greatest common factor between these two. So I'm going to factor the 3 out, which leaves me with an x squared minus 4. And now from here, I'm not quite finished because x squared minus 4, that's my difference of squares. Remember, a difference of squares always factors into conjugates. One's a plus, one's a minus, so it factors into x plus 2 and x minus 2. And that 3 just kind of tags along for the ride. So it's 3 times x plus 2, x minus 2. And now that one's factored completely. Number 21, this is a difference of cubes. They're both perfect cubes and they're being subtracted. And whether it's a sum of cubes or a difference of cubes, remember we follow SOAP. Same, opposite, always a plus. And that helps us when we're setting up our signs. Remember, it's a binomial and a trinomial. The first sign is the same. This was a minus sign, so our first sign is also going to be a minus sign. The next sign is the opposite of that, which is a plus sign. And the last sign is always a plus, so it's another plus sign. And now I start off, I kind of take the cube root of what I have. The cube root of x cubed is an x. The cube root of 27 is a 3. Okay, it's what to the third power will give me those two things. So it's an x and a minus 3. And now I just make it work. This first term here times this first term. When I multiply those, it's going to have to equal the x cubed, which means this is going to have to be an x squared. This term times the last term here is going to have to equal the 27. So this is going to have to be a 9. And then the middle term, I just take the two values that I plugged in over here for my binomial, the x and the 3, and I multiply them together. X times 3 is a 3x. So now I have my factor x minus 3 and then the x squared plus 3x plus 9. Okay, and the sum of cubes works exactly the same way. For this one, it asked us to solve, and the first way we always check to see if we can solve something is by factoring. So I build a bridge, that's a negative 8. The two magic numbers that I'm looking for are positive 4 and a negative 2. They multiply negative 8, add to a positive 2. So this one can be factored. In fact, I can use my shortcut, so it's x plus 4 and an x minus 2. And now I can set each factor equal to 0. So here I subtract the 4 from each side, and I find out that x equals a negative 4. Here I add the 2 to each side, and find out that x equals a positive 2. So those are my two answers, and that's it. In number 23, I'm going to start off the same way. I'm going to build a bridge. I build a bridge that gives me a negative 5. And then I'm trying to think of two numbers that multiply to negative 5 but add to a positive 2, and it's just not going to happen. These two numbers don't exist. So that means I have to find a different method. I'm going to do this one twice. The first method I'm going to look at is completing the square. And for completing the square, the first thing I want to do is I want to move the constant term to the other side of the equation. So I'm going to add that 5 to each side. So I get x squared plus 2x with a little space equals 5. I know the next thing I want to do is complete the square, so I take that b value, the middle term, the 2, I divide it by 2 and square it, which gives me a 1. So I do a plus 1. Whatever I do to one side, I have to do to the other side. And now I'm going to factor this perfect square trinomial that I've just made. It factors into an x plus 1 squared. Over here, 5 plus 1 is a 6. Now I take the square root of each side. So that's going to give me an x plus 1 equals. Since I took the square root of each side, I have to remember to do plus or minus that square root. So it's plus or minus the square root of 6. And now I subtract the 1. So I find out that x equals a negative 1 plus or minus the square root of 6. And that's my answer. There's two irrational solutions there. That's one method for doing this. The other method would be to use my quadratic formula, the opposite of b plus or minus the square root of b squared minus 4ac all over 2a. So the opposite of b, that's going to be a negative 2 plus or minus the square root of 2 squared minus 4 times a, which is 1, times c, which is a negative 5, all over 2 times a, which is 1. So now I've got negative 2 plus or minus the square root. That's going to be a 4 plus 20. And be careful with your signs there because we're subtracting and there's a negative thrown in there. It ends up being minus a negative, which is plus a positive, all over 2. So that's going to be a negative 2 plus or minus the square root of 24 all over 2. And I can keep simplifying this thing. So I've got negative 2 plus or minus the square root of 24. I can break down into 4 times 6. The square root of 4 is a 2, so it jumps to the outside. It's a change number on the outside. So it's 2 root 6 all over 2. And now I can see a common factor of 2 between all of these. So I can divide this. Negative 2 divided by 2 is a negative 1. The 2 divided by 2 is a 1, so it just leaves me with the square root of 6. And you notice I get the same answer either way. So whichever method you prefer, most of you are probably going to want to do the second method of just using the quadratic formula. But completing the square is a great option when you have an a value of 1 and a b value that's even. Okay? Number 24, the first thing I'm going to do is rewrite this in the notation that makes a little more sense. F of g of 2. And now I start what's inside the parentheses here. The g of 2, I can take that off to the side. G of 2 equals, well, g of x is x squared minus 5, but instead of x, whatever's in these parentheses, that's what I plug in for x. So I plug a 2 in for x. So that's going to give me a 4 minus 5, which is a negative 1. So that means that this thing right here, the g of 2, is actually equal to negative 1. So I'm going to replace it with a negative 1. And now f of negative 1, f of x is x plus 2, but instead of x, whatever's in the parentheses, I plug in. So I plug the negative 2 in, and that's going to give me a positive 1. So f of g of 2 equals 1. I do something very similar with the next one, except this time I'm doing g of f of x. So I'm doing g of f of negative 4 this time. And once again, if I take this off to the side, give myself some space, f of negative 4, well, f of x is x plus 2, but instead of an x, I'm going to plug in a negative 4. So it's negative 4 plus 2, which is a negative 2. So really, this equals a negative 2. So now I have g of negative 2. Well, g of x was x squared minus 5. But instead of an x, I'm going to plug in a negative 2. So I've got 4 minus 5, which is a negative 1. So g of f of negative 4 is actually equal to a negative 1. Okay? For these, whenever we're given a list of ordered pairs and we're asked to do the composition or the inverse, our answer is also going to be a list of ordered pairs. So for this one, I've got g of f of x, which means I'm going to use the x values from the f function, which means I'm going to use the 3, the 2, and the 1. And now from here, I'm just going to kind of form a chain reaction. When I plug a 3 in, the f function spits a 5 out. And I'm going to plug that into my g function. When I plug a 5 into my g function, I get a 2 out. So I started with a 3, I ended with a 2, so it's the ordered pair 3, 2. Now I do the same thing with the next one. The 2 connects me to the negative 2. Over here, the negative 2 connects me to the 1. I started with a 2, I ended on a 1, so it's 2, 1. And then the last one, the 1 connects me to the negative 3. The negative 3 connects me to a 3. So I started with a 1, ended with a 3, so it's 1, 3. So that's my composition g of f of x. And if I had f of g of x, I would start with the x values from the g function instead. Okay? For number 27, I want to do the inverse. That's what this symbol means. I want to do the inverse of f of x. So instead of taking f of x exactly as it's written, the inverse, remember I just switched the x and the y values. So I take each of these ordered pairs. The first one was 3, 5. Instead, I'm just going to switch the x and the y. So it's going to be 5, 3. The next one, instead of 2, negative 2, it's going to be negative 2, 2. And the last one, instead of 1, negative 3, it's negative 3, 1. And that's it. That's my inverse. So composition, I plug one function into the other function. Inverse, I switch the x and the y.